The Antarctic ice looks empty at first. A flat, white silence broken only by wind and the distant crack of moving floes. Then the water shifts. A dark shape rises beneath the ice, moving with a confidence that feels almost deliberate. This is not the clumsy predator we expect from such a frozen world. It sings underwater. It hunts with strategy. It feeds on prey that should be far beyond its size. Today, we're diving into why nothing about the leopard seal fits the rules we assume govern life in extreme cold, and how evolution shaped one of the most unconventional predators on Earth. In Antarctica, survival usually follows a narrow script. Energy is scarce, seasons are brutal, and most predators specialize tightly to avoid waste. Crab-eater seals focus almost entirely on krill. Weddell seals dive deep for fish beneath stable ice. Even apex hunters like orcas divide themselves into distinct ecotypes, each targeting a specific kind of prey. Efficiency here is not optional. It is enforced by cold, darkness, and long winters. The leopard seal does not follow this script. From a moment biologists began systematic observations in the mid-20th century, something fell off. Leopard seals were not restricted to pack ice like most Antarctic seals. They appeared alone, patrolling vast stretches of open water and ice edges. They hunted penguins with ambush tactics, more typical of big cats than marine mammals. Then they were seen consuming krill, tiny crustaceans normally filtered by much smaller, highly specialized seals. Ecologically, this places the leopard seal in a strange position. It is both a mesopredator and an apex predator, depending on context. It preys on penguins, fish, squid, and other seals, including juveniles of species nearly its own size. Yet in other seasons, it shifts downward in the food web, feeding heavily on krill when larger prey becomes scarce. Stable isotope analyses of leopard seal tissues confirm this flexibility, showing dramatic seasonal swings in trophic level rarely seen in mammals. This flexibility comes at a cost. Leopard seals are large. Females can exceed 500 kilograms, making them energetically expensive animals in an ecosystem where calories are unpredictable. Most Antarctic predators reduce risk by synchronizing their feeding with seasonal abundance. Leopard seals, instead, spread risk across prey types, habitats, and hunting strategies. They move between pack ice, fast ice, and open ocean, following opportunity rather than structure. Field researchers working on the Antarctic Peninsula often describe leopard seals as out of place everywhere, yet successful everywhere. They are not bound to breeding colonies like penguins, nor to breathing holes like Weddell seals. Their presence feels deliberate, almost strategic, as if the animal is testing the environment rather than submitting to it. Evolution rarely produces generalists at the top of extreme ecosystems. Yet here, in one of the harshest environments on Earth, the leopard seal thrives by refusing to specialize. That contradiction is the foundation of everything that follows. A leopard seal's skull does not make sense at first glance. It is long and powerful, built for gripping large, struggling prey. But when the jaws open, the teeth tell a more complicated story. Instead of the simple, conical teeth typical of predators that seize and tear, leopard seals possess elaborate cusps that interlock when the mouth closes, forming a living mesh. This structure is not an accident. It is a rare evolutionary compromise, one that allows the same animal to hunt penguins and filter krill. Among Antarctic seals, crab-eater seals are the specialists. Their teeth form a near-perfect sieve, evolved almost entirely for straining krill from seawater. Leopard seals share part of this design, but not its full commitment. Their teeth are sharper, spaced wider, and anchored to a jaw capable of violent force. When feeding on krill, the seal closes its mouth, expels water through the tooth lattice, and retains prey. When hunting larger animals, it uses the same teeth to grip, shake, and tear, Fossil evidence suggests this duality emerged through gradual modification rather than sudden innovation. Early pinnipeds show increasing dental complexity as Antarctic ecosystems became more productive during the Miocene and Pliocene. As sea ice expanded and krill populations exploded, a new opportunity emerged: filter feeding in cold water. Most lineages chose one path. Leopard seals took both. This anatomical compromise carries trade-offs. Leopard seals are less efficient krill filters than crab-eater seals and less specialized hunters of large prey than orcas. But evolution does not reward perfection. It rewards survival across uncertainty. When penguin colonies disperse or ice conditions change, leopard seals do not starve, they switch. Researchers examining tooth where patterns find evidence of this seasonal flexibility etched directly into enamel. Years dominated by krill feeding leave different where signatures than years heavy invertebrate prey. In this way, the leopard seal's teeth become a biological record of environmental variability. In extreme environments, anatomy often narrows. Here it broadens. The leopard seal's dentition is not optimized for one job, but for resilience across many. And in Antarctica, resilience may be the most powerful adaptation of all. Physical adaptations explain how leopard seals eat. They do not fully explain how leopard seals behave. Unlike most Antarctic predators, leopard seals regularly display curiosity, an unusual and risky trait in extreme environments. Divers and researchers have documented individuals approaching humans slowly, circling, observing, and sometimes mimicking movements in the water. These encounters are not consistent with simple territorial defense or feeding behavior. They suggest assessment. Underwater acoustic recordings reveal another layer of complexity. Leopard seals produce long, structured vocalizations during the breeding season, songs with repeating patterns that can last for hours. These vocal displays are learned, not purely instinctive. Individual seals modify their calls over time, indicating a capacity for vocal learning previously associated mostly with cetaceans. In ecological terms, intelligence is expensive, brains consume energy, and curiosity increases exposure to danger. In Antarctica, most animals minimize risk through rigid behavioral rules. Leopard seals appear to do the opposite. They explore, they test, they adjust. This behavioral flexibility becomes most evident during hunting. Leopard seals do not simply chase penguins. They ambush them at ice edges, manipulate waves to knock prey from flows, and sometimes toy with prey, not out of cruelty, but control. High-speed camera studies show seals adjusting their strike angles and grip strategies based on prey size and resistance. These are not fixed patterns. They are responsive decisions. Such behavior may explain why leopard seals can exploit prey types that fluctuate dramatically year to year. When ice conditions disrupt penguin breeding success, seals shift tactics. When fish populations move deeper, seals dive differently. Learning allows them to respond faster than genetic adaptation ever could. But this intelligence carries consequences. Behavioral risk sometimes leads to fatal mistakes, attacks on unfamiliar prey, aggressive encounters with larger predators, or conflicts with humans. Evolution tolerates this because the net gain outweighs the cost. In the leopard seal, survival in the extreme is not achieved through caution alone, but through calculated curiosity. It is a strategy that only works at the edge of biological possibility, and only for animals capable of adapting in real time. Antarctica's food web is dense but uneven. For a few months each year, life explodes. Krill bloom, penguin colonies swell, fish rise closer to the surface. Then the system contracts and energy becomes scarce again. Most large predators respond, synchronizing their lives to these pulses. Leopard seals do not coordinate. They operate alone. Satellite tagging studies reveal just how solitary this strategy is. Individual leopard seals range across thousands of square kilometers, moving between ice edges open water, and coastal zones with little overlap. Even during peak feeding periods, they rarely hunt cooperatively, where other predators reduce energetic cost through group behavior. Leopard seals rely on reach and adaptability. This solitary existence places extreme pressure on energy balance. A large female requires an enormous caloric intake to maintain body mass, reproduce, and survive long winters. Rather than specializing in one predictable prey, leopard seals spread their hunting effort across multiple ecological niches. They dive deep for fish, surface hunt penguins, skim ice edges for krill, and opportunistically prey on juvenile seals when conditions allow. Physiologically, this requires exceptional versatility. Leopard seals possess high oxygen storage capacity for deep dives, yet also show muscle fiber compositions suited for explosive surface attacks. Their metabolism is tuned not for efficiency in one mode, but for rapid switching between many. This flexibility is rare among mammals and nearly unheard of in polar specialists. The cost is exposure. Solitary hunters cannot rely on group defense. Leopard seals occasionally fall prey to orcas, particularly when caught away from ice. Their broad range increases encounters with risk as much as opportunity. Yet population data suggest this strategy remains viable, at least for now. In a system where abundance is brief and scarcity is long, leopard seals choose independence over coordination. It is a high-stakes evolutionary gamble, one that has allowed them to persist where specialization might fail. Adaptation is often framed as a solution. In reality, it is a balance, and in extreme environments, that balance can be fragile. The leopard seal's success rests on flexibility, dietary, behavioral, and ecological. But flexibility does not mean immunity. As Antarctic ice patterns shift, the very unpredictability that once favored generalists is changing its shape. Seasonal sea ice now forms later and breaks earlier in many regions. Penguin colonies relocate or decline. Krill distribution becomes less stable, influenced by temperature, acidity, and ice cover. For a predator that relies on switching strategies, these changes introduce new limits. Leopard seals cannot simply adapt infinitely. Their large bodies still require large energy returns. If prey becomes consistently smaller, deeper, or more dispersed, versatility may no longer compensate for cost. Scientists monitoring body condition over decades have already observed regional differences. Some populations appear robust, others leaner, suggesting local ecological stress. There are also limits to learning. Behavioral flexibility allows individual seals to adjust, but it cannot rewrite physiology overnight. Teeth designed for both filtering and tearing are not perfect at either. Muscles built for explosive ambush are not optimized for endless deep pursuit. Evolution's compromises work best in fluctuating systems, not in steadily declining ones. Perhaps most importantly, much remains unknown. Leopard seals are among the least understood large predators on Earth. Their population size is uncertain. Their breeding success is difficult to measure. Their capacity to pass learned behaviors across generations remains an open question. The leopard seal exists as proof that life can resist rigid rules, even in the harshest environments. But it also reminds us that adaptability has edges. Beyond those edges lies uncertainty, not just for one species, but for the fragile balance of an entire polar ecosystem.